All right. In our new video, we are going to be doing the interesting part where we really get to understand how our WebAssembly binary format works. And that's going to be by traversing the AST that we've constructed. We can see we have the logs down here for our AST. We're going to traverse it and we're going to be emitting bytecode as we do so. Um, so the way that we're going to be doing that is following three things. Over here, we have a reference that kind of just lays out, specs out the binary format. WASM reference manual by Sunfish Code, although it's got 6 contributors. And then there's this other one over here as well that, kind of describes in English. The other one's pretty good English as well, but they both go into really good detail about how all of the mechanics work for generating our bytecode. And then over here, there's actually a demo where we can compare how our bytes are working against the bytes over here. So yeah, let's go ahead and get started. I guess the first thing that we'll do is we'll make a compiler file. And let's make a function called compiler, and it'll take an AST. We'll need to use AST, and it's going to spit out a vector of U8s. And yeah, we'll just start off by and there's some boilerplate at the beginning that I'm going to snag here, and let's return our bytes. Then over in main, we can compiler, and let's let our bytes be compiler, our compiled AST. And I'm going to steal some stuff for formatting. And let's print this out and make sure that we're getting our things that we expect. Okay, and actually, that's a tight little string down here, so I'm going to not join for the time being. All right, and so we see all of our bytes. Granted, they're not formatted exactly the same way, but I think we'll be able to make do. And so here, it's kind of aptly named WASM binary magic. This is kind of just signifying to the WASM time runtime, or whatever our host's runtime is, that we are indeed looking at a properly formatted binary file. The next thing that we're going to do is we're going to, look at our type section. So basically, kind of the layout, we're not using all of the functionality of WebAssembly for our 3 functions that we have, so we're not going to have to implement all of these sections, but we're going to do a decent number of them. And so basically, a section at a time, you kind of have an encoding of pieces of information in your abstract syntax tree. The very first one is a type section, where a type here is going to be the type of function signature, basically. So we have 3 function signatures. We have one where we have 2 i32s as input, one is output, one where we have 4 as input, one is output, and one where we have 3 as input, and then 1 as output. And the way that these typically go, each of these sections, is you have one code that identifies which section you're writing to, and then like the number of items that are in it. There's always this, here in this demo, there's always this section size, which then at the end of the section, they kind of go and fix up. And we're, to really actually get the WASM time runtime to work, we don't include this guess, and we just calculate the correct size at the very beginning and put it in. And so then here, basically, there's like a 6-0 that identifies that it's a function. We comment on the number of parameters, which is 2. Then 7f represents an I32. The number of results for us is always going to be 1. You can have more than one result in a wat function, but all the functions that we have only have 1, and 7f. And then you do the same thing for the second function, so the type, and the same thing for the third function type. The next section is going to be the function section, where we go through and we actually end up referencing the signatures that were defined in the first type. So here, there's not that much benefit given our functions, because we only implement a function of each signature one time. So we're kind of just going to be, you can already see we have one function that uses the first one that uses the second one uses the third one. But you can imagine that we could have a function that does subtract 2 and a function that does multiply 2, and we could have multiply 4 here and multiply 3 here, in which case we would see these signature indices. Basically, the order in which we encounter the function signatures would represent which index, or would determine which index that we have for each function signature, and then you would see us referencing multiple at the same time, and that's saving ourselves work. Unfortunately, ours is really simple, and so we don't get to actually see much of a benefit of that. But in general, there is one. So I think that the next thing that we should do probably is define a struct for function signatures. And so we are going to call it struct sig, and it's going to have 2 attributes. It'll have a slice of wasm primitives and a result. And again, this could be a slice generally speaking, but because all of our functions we know, maybe later on we'll do more videos where we make this more rich. Maybe this will just remain a small lesson for doing one little bit of functionality end to end. I don't really know yet, but yeah, we need lifetime parameters here. Okay, and let's also define how to make a new one of these. New, and that'll take a function which will be an AST function as defined in our prior videos, and we'll return a sig this is going to return a self. And then our sig is going to have params, which come from our function params, and a result that is going to be our function result. And we probably have some lifetime stuff going on here. So why don't we, let's do this, which means that we're going to need to do this. And this. Okay, and then here. Okay, and we need a copy trait for our wasm primitives, which we can do. So wasm primitives, we probably need a clone. Okay, and let's see. So now let's make a vector of signatures. So let's new, and it'll be able to deduce a little later on that it's sigs. So for each of our functions in our AST module, we are going to push a new this. Actually, wait. Let's do let me think for a second about how we want to do this. Oh, because AST.module, we need to reference differently. Let's do perfect. Okay. And yeah, so as we were saying before, the first thing that we typically do is we need the number of things that there are. So there are three types, aka function signatures. And here we could go through our vector and check for duplicates for each one. I think that rather than iterating through as we build it, we'll probably be better off if we just do a dedupe, which we can do on vectors provided that you've implemented quality in the thing, because you need a way of comparing items in your vector to make sure that they are to see whether or not they're duplicate. Okay, and bam, that is that. So we also need to know what the size is now, so we can let also first let the number of types equal, that can just be our sig's length. Let's let our, now we need to calculate the actual size of the entire sig section. So for that, we're going to iterate over and do a little bit of functional style things. So here fold is basically very similar to like a reduce function in several other languages. We're going to do an anonymous function here, so it'll have an accumulator and a current, and this will make more sense in a second. We're going to do our accumulator plus 4 plus our current params length, and then we'll add 1, and all of that. Let's see. Okay, so let's take a look at that then. So here, for each of these, we're going to have a basically how many things are in here, as well as our 6-0 indicating that we're a new type, and our 0-1, which is our number of results, and here this is our number of params, and yeah, also we have our number of results here and our I32. So that's where our items are coming from. Hopefully that was clear. I might be able to make it a little bit clearer at the end as well, after we've gone through the whole thing. But so, yep. Now we can do bytes push, and at the very beginning, I think I forgot to do just the one that indicates that we are a section code. So here we can do, or actually we did already do that in our binary, in our magic. Here's our magic, and it ends after with our 8 bytes of magic. We have our 0-1 indicating that we're doing a type section. So yeah, now we can do bytes push. This will be our type section size. and our number of types. And common theme here is going to be that we have a U size and that we need it to be a U8. And let's see what's wrong. Oh, I think over. Boom. Okay. All right, so now let's talk about actually writing each of these things. So the first thing that we're going to do is, well, let's actually for our sig, let's implement a function for writing bytes or for emitting bytes. So we'll do pub function write, and this will take this, and then we'll also need a mutable reference to bytes. Over here, and we don't need to return anything. Okay, so the very first thing that we do is we push 0x60, and then our number of params, which is just going to be bytes push self params length as a U8, and then for each of our params, we need to actually put what kind of param it is. So for param in self params, we are going to match on our param, and then we'll again if you watched the prior video, there are 4 different WASM primitives, but we're only ever encountering one, and so for this video we're only ever implementing one. So we'll push the code for an I32, which is a 7F, which is in those specs that I referenced at the beginning, and then otherwise we don't need to do anything. We can just continue. Okay. Next, we need to do something similar for our return values. So here we're going to do bytes push 0x01, which is our number of parameters, and then we are basically just going to match on our results. So if we have a WASM primitive I32, then we will push another 7F. Okay. And that should actually do it. So over here now, basically, for all of our SIGs, we're just going to write. Right, and if we do this now, this looks pretty similar. Again, it's not formatted quite the same way, but we have 60 and then our number of params, 60, number of params, 2 7Fs, 1 result, another 7F, and then another 60 for the next type, 4 7Fs. And yeah, it looks like we have handled our function signatures properly. So now we can move on to the next section, which is our function section, which is we do also, we don't need to do our fix up because instead we did our fix up right here where the guess happened. So yeah, let's go ahead and push our 0x03 to kick off our function section. So with all these, basically, the very first thing that you have to do is figure out how many of your thing you have. We have three functions, and again, this would be where if we had like a multiply 2 and a multiply 4, we would see that we had more functions than we do signatures, and we would end up re-referencing our signature indices. So let's do our number of functions. BRAST module length. Okay, and let's do sorry, one moment. First we need to do our section size. Our section size here is going to be our number of signatures plus one more. So we're going to do our number of sigs, or sorry, number of functions plus one, and then our number of functions. And we probably need okay, cool. So now, for each of our functions, we are then going to yeah. So here, we're going to iterate over our sigs as well and figure out which index. So find out the index of the sig of this function in our sig index stack. So here we have for our sig in sigs. Now the thing is that we're also going to need the index, which we can get if we turn this into an iterator and enumerate, and then do I like this. Okay, and check whether our sig is equal to our what happens if we make a sig out of our function. And if that's the case, or what, so that should happen only for one because all of our signatures are unique because we deduped up above. Then we will push the index as a U8. And I think we've got a few things here. First, let's do, first this is a func. Oops. That's the name of it. Also, we want to see if they're equal, which means that we're going to need to so one of these is a pointer and the other one is not. So let's, or sorry, as a reference. So let's do one of these. Okay, I think we're going to need to do this like we did above so that we don't give up ownership. And for our sigs, I think that maybe somewhere up above we accidentally gave up ownership of our sigs. Let's see. we should be able to iterate over SIGs, I think. So somehow in our construction of SIGs, we ended up giving up ownership, and so the question is just where did that happen? Here. Boom. Sorry about that. So now we should be able to keep going along. So if our sig, bam, 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 and that should actually be everything that we need. And in fact, we see that we have one type that is 0, one type that is 1, and one type that is 2. And yeah, so now we can keep going along. So the next one is the export section. So if we come over here and we look at our exports, the very first thing that we do is we well, first we'll find out how many exports we have, because exports are optional. We don't necessarily need to have exported every function that we have. So first, let's determine whether or not we need an export section. So we'll do let the number of our exports be. So we'll go through our AST module. We will iterate and we will filter. And here we will do a func export length greater than 0, and count how many things are left. So now if our number of exports is greater than 0, we will signify that we are beginning to write a export section. And now let's go through and define all the names. So our export names will be our AST module, iterated over, or iterated, turned into something that can be iterated, and then our anonymous function will do export, and then we can collect all of those into a vector. Okay. Then we also need to do our export section size. So let our export section size, this is going to look similar. AST module iterable map f to our export. And now we'll do another fold where we're building something up. So we'll have an initial value of 0. We'll have an accumulator and a current item. And here we will do our accumulator plus our current length plus 3 is what we need in order to come out right, I think, which we can reason about here in a little bit. So we'll do, then our bytes will push our export section size plus 1, and that is as a U8. And then our number of exports. So we'll go through this in a second and think about it a little bit more. It's kind of weird because you have to figure out the length of these things before you actually go through and then put things together, but we can think about this. So our number of exports is 3, and so basically we have our string, we have one coming from our string length, and then we have length that is actually coming from each of the characters. There's then an export kind, which for us, I think is defined. Basically, it's coming from the fact that the thing that is being exported is a function. Um, so that's what the 0 is here, and then we have our function index, and then the actual length of our string. I forgot right there. So that's where those additional numbers are coming from in our fold, and then yeah. So now we can go do our for loop and actually add our characters. So we're going to do an enumeration again. If we have, well, so if we might not have a an export, in which case we'll continue. Otherwise, we will first push the length of our export. And then this is, we get to do a little bit of ASCII stuff here. So for the car in our export as bytes, we will, I could pull up an ASCII table right now. The main thing is that we have to push it as an ASCII, either lowercase or uppercase, and there's 2 different Rust functions for that. So we'll know that we're in our range for lowercase if the car is greater than or equal to 97. And that's for lowercase, and then else. And this will be low, upper. Okay. And then we will do a, this is our type, and then as your 8. And then that's our function index again. And I think that I'm realizing right now that there's an error here that's working only because of the specific wat file that we have. Yep, actually can't trust that our export will preserve the order of the initial function signatures that we encountered. So for now, we're just going to acknowledge that these bytes that are being emitted will only work in a certain way because I am re-implementing something that's already been implemented. But maybe I'll make another video at some point where we go through and we actually handle the more general case. Cool. Next up is actually, I think, the last one that we have to worry about. And that is our code section. So this is where we actually have the instructions that are in our functions. So the very first thing that we're going to do is push bytes push 0x0a. And let's calculate the length of our body section. Length. It's going to be, again, we're going to go through our AST module, which is a list of functions. Turn it into an iterator. Map f body. And actually, sorry, this isn't our section length. It's a body length. Actually, I might have been wrong. Hang on. Let's do our fold. 0. We are going to do our total length and our current body for our accumulator and our current. And here we're going to do all length plus current body length plus 3 and do 1 at the end of that. So yeah, no, this is our body section length. And I'll name it accordingly. Okay. And now we can go ahead and add our body length as a U8. And we'll also do our AST module as U8 and body section. Okay, and so we can come back over here and look a little bit. So for each one of these, we'll have a local declaration count. Again, we're doing something that's a little bit specific to the Watt that we're compiling because we're not declaring any local variables. We're just getting them from all of our local gets are referring to parameters. So yeah, then we do a local get with the indexes, a local get with the indexes. So these are all contributing to our length. We have a B that signifies our that we're at the end. So I think that our body size, our declaration count, and our end is what is going to be responsible for that 3 over here, and then that 1 is typically like it's either the number of functions. Yeah, I think it's the number of functions. Okay, so let's go ahead and go through our body. So here, let's define a vector. Let our bodies be our AST module, iterated map, and this will be f turning into our function body, and we'll collect that into a vector. Let's do some iteration. So for our body and our bodies, so actually you would think that this might be challenging, but it's not so bad. So the first thing is to push the length of this function's body. So that's going to be bytes push body length plus 2, and that's going to be as a U8. So again, those 2 are coming from our declaration, number of declarations, and our length. And then so here's our pushing our local declarations. And then for each instruction in the body, we will match on the instruction. And there are several instructions here, and luckily, and we need this to be as an str. There are a lot of these. So, and that's because we're going to be just we're matching on an str. So local get has a specific code in those references, which 20, and there's also we're adding I32s, and that one has a different code, which is 6A, and then our general case will be we get to assume, because of our limited WebAssembly support, that it's referencing one of these parameter indices. So here, just for byte in our instruction as cars, we can just push string from our byte and have that parsed as a U8. And let's handle our errors. Okay. And I think, actually, after that, the last thing that we do in our body, so this is inside of our for loop, inside of our outer for loop, we are doing a push to signify that we're at the end of the function body. Okay. So, do we have errors? Here's the moment of truth. We might have to compare this to the functioning implementation that we have already. Let's try and write this out. So to write this out, we are going to let mute file equal add for wasm dot unwrap, and we will do file write our bytes. Let's give that a whirl. All right, so here's all of our bytecode right here. It's also written to this not human readable file. And if we did this correctly, wasm time, our file, we want to invoke a specific function, and we got 3. And similarly, instead, we could reference the add for function, and we get 10. So we've successfully written a WASM executable that is able to be read by mainstream, the kind of the de facto WASM runtime. And when we've gone through all the steps for how one of those is generated from our WebAssembly text format. This project probably won't turn into anything. It's not like intended to be something that people really use. It's more so done for people who want to understand how WebAssembly works a little bit more under the hood. If there are other things that people would like to be implemented, I mean, there's plenty of WASM syntax that we did not cover here at all. But yeah, I'm not sure what kind of video I'll be putting up next, but I hope to come up with a good idea and put something out pretty soon. Thanks for watching.